Hi guys, today I'll be showing you how to diagonalize a 3 by 3 matrix. So we've been given C, right, as this matrix, and we have a linear operator T in this case from R3 to R3, and we've been given the standard matrix of T, which is equal to C again. So we have to diagonalize T over R and find a new basis B for R3, for which T in the basis B is diagonal. So we start off by finding the characteristic polynomial for C. So if we first copy C down, C would be 5 0 0 minus 2 2 0 4 6 negative 3. So we find C minus lambda I in our case, and the determinant of that to equal 0. So we have in our case 5 minus lambda minus 2 4 0 2 minus lambda 6 0 0 minus 3 minus lambda. Just a very quick aside, we can see that this is a upper triangular matrix because we have all non-zero entries as above the main diagonal of the matrix. So we know from before that the eigenvalues of this matrix are 5, 2 and negative 3. But we'll find that using the characteristic polynomial. So we evaluate this determinant now and we check for this condition. So we take 5 minus lambda, then we multiply 2 minus lambda and 3 minus lambda minus 0. Then we take plus 2 because there will be a negative. So we take plus 2 and then we find, because we have 1 1 1 2 and 1 3, right? So if we have negative 1 to the power 1 plus 1, which is 1, negative 1 plus 1 plus 2 is negative 1, and negative 1 1 plus 3 is positive 1. So it becomes plus 2. We covered this and this, right? So we get 0 again for multiplication. Yeah, I think we get 0, yeah. And then we have negative 4. Sorry, this is negative 4. And this would be 0 again, which gives us 0. So now we have 5 minus lambda, 2 minus lambda, and this is minus 3, sorry, is equal to 0, right? Now we observe that we would have 5 minus lambda 0, 2 minus lambda 0, minus 3 minus lambda 0. So lambda is 5, lambda is 2, lambda is negative 3. These are our eigenvalues. Now we find the corresponding eigenvectors. So we had an initial matrix as C, so we have C minus 5i now, where we had C earlier as 5 0 0 minus 2 2 0 4 6 negative 3 minus 5 0 0 0 5 0 0 0 5. This would be subtracting everything from the diagonal now. So we have 0 negative 2 4, 0 negative 3 6, and we have 0 0 and negative 8 now. Now we have to find the rref of this matrix. So I could divide by 2 now, the rref of this matrix. So if I divide the first row by 2, I would get 0 negative 1 2. Second row by 2 is 0 negative 1 2. Third row by negative 8 would 0 0 1. Then I can add the first, subtract the first row to the second row. I would get this. Then I could swap, so I would get this, and I could multiply this by negative 1, so I could get this, right? This is the case when we have 5. So have I done something wrong? I'm not too sure, but I think it's all right. We could let x1 be t as a free parameter because there's no pivot in the first column. Then we have x2 minus 2x3 equals 0 and x3 equals 0. So x2, because these are pivots, right? So x2 would be minus 2 times 0 is 0. So we have t 0 0 as our standard solution for the system. So we would have our corresponding eigenspace as 5 and 1 0 0, right? This would be a corresponding eigenspace for a particular vector. Now similarly, we could find the eigenvectors for the other two matrices by finding, in our case, c minus 2i and c plus 3i, right? So for this we would have 2/3 1 0. This is this beforehand, and I would get minus 3 minus 4 minus 6 5, right? Is 5. So these would be our corresponding eigenspaces. Now we need to, we've been given that for our initial matrix, which is C, right? So we have three sets of eigenvectors, right? Set of three eigenvectors, which would be, let's say we could call it B, right? This would be 1 0 0, 2/3 1 0, -4 -6 5, sorry, yeah. And we can observe that this is linearly independent. Why? Because if we make this as a matrix, right? So we have 1 2/3 -4 0 1 -6 0 0 5. If we divide the last row by 5, we would get 1 here, and we would have pivots in, we could do rref and remove this, and we would have pivots in all three columns, right? So this is a linearly independent matrix, which makes these three components themselves linearly independent. And therefore, we know that the basis, what's itself in the definition, is supposed to be linearly independent, consists of three linearly independent vectors, which in our cases are our eigenvectors also. So we take any matrix, let's say P in this case, we normally take P from notation 1 0 0, 2/3 1 0, -4 -6 5. And now we compute P inverse. Right, so P inverse is found by taking 1 by determinant of P times the adjugate of P. The adjugate of P is very simple. You cover the first element and take the product of the remaining elements. So if you cover this row and this row, this row and this column, you would take the product of these two elements and multiply by this, the coefficient of the product of the row and column numbers. So you have -1 to the power 1 plus 1 for this. For 2/3 you would have -1 to the power 1 plus 2. For -4 you would have -1 to the power 1 plus 3, and so on and so forth. So for 0 you would have, -1 to the power 2 plus 1, and so on. So you do this calculation, you find the inverse of the 3 by 3 matrix, which in our case would probably be, which I found to be 1 0 0, -2/3 1 0, 0 6/5, and 1/5. This would be a P inverse, right? Now we know that P inverse times the matrix T in our case times P should give us the diagonal matrix of TB, right? So we have 1 0 0, -2/3 1 0, 0 6/5 1/5 times 5 0 0, -2 2 0 4 6 -3. This is our T of E, which is given to us here, right? This matrix. So we take that and we do the calculation here, and we have a third matrix as 1 0 0, 2/3 1 0, -4 -6 and 5. So we multiply now. So if we multiply the first two, which is these two matrices, you would get 5. This times this. So how do we multiply? We take this and this. We multiply this, this, and this. Now we have 5, right? 1 times 5 plus 0 times -2/3 plus 0 times 0. In this case, we have -2. Yeah, I think that might work. But we could multiply. It's better if you multiply the remaining two. It's good to have a last matrix to us. So we could multiply this and this first. So we would get this first matrix as it is. And now we have 5 times 1, 0 0. Okay, so if we have 5, then we have -2/3, so 4/3. Then we have 4 3s are 12. We have 0 here, then we have 2 2 cells and 2 18. Now we have 0 again, and 0 0 0. Then we have 3 times negative 3 times 5, which is negative 15, right? Now if we expand this, we have 5 0 0, so we have 5, we have 4 thirds minus 4 thirds 0, so we have 0, we have 2, then we have 6 18 minus 12, okay, 2 18 6 negative 12. This should be 0 no 4 thirds 12, oh 1, this is 12, sorry, not 2, I think, yeah, sorry about that. This is 12 minus 12 plus 0, so, and now we have 0 0 and 0, we have 0 2 and 0, we have 0 15 negative 15 0 again. Now we have 0 over here again because we have 0 0 and 0, then we have 0 again, then we have negative 15 by 5, which is, yeah, so we have this at the end, 5 0 0 0 2 0 0 0 negative 3, which is basically diagonal of lambda 1 lambda 2 lambda 3, which we earlier found to be 5 2 and negative 3. They all have algebraic multiplicities of 1, 3 is equal to 1, and we can also determine the geometric complexities in our case depending on the free number of parameters. So in our first case, when we found the eigenvector, there was one free parameter, so the geometric multiplicity of this should be 1, and similarly we could find them for other two eigenvectors. There's a formula which is important. This is always holds true for any matrix because this is basically the dimension of the null space of the eigen e lambda I, right? So that's how you find it, and yeah, it's basically how many number of free parameters you might have to find the null space of any eigenspace, right? So that's there, and that's how you do it. This is the full calculation, so I hope you understood some part of it. Thank you.